Section 5.2 of Anton is on diagonalization. So let A be an n by n matrix, and diagonal matrices are matrices whose only non-zero entries are along the diagonal. Everywhere else, so where there's nothing written here, is a 0. And they're interesting for a variety of reasons. One is that they're easy to compute with, and in particular easy to multiply with. If you multiply two diagonal matrices, their respective entries just multiply. Anyway, starting with the matrix A, in this section we're going to find an invertible matrix P, if we can, such that P inverse times A times P is a diagonal matrix. Now, this is a pretty strange combination to think of, but it turns out when you're changing your basis, this is how the matrix associated to a linear transformation changes. But we'll worry about that later. Right now, we're just trying to find out how to find such a matrix P so that when we multiply by P inverse on the left and by P on the right to a matrix A that we start with, we get a diagonal matrix. Now, it won't always be possible, but if there exists such a matrix P, then we say that the matrix A that we started with is diagonalizable. Now, the trick to cook up P is that P is going to be the matrix whose columns are the eigenvectors of A. Now, let's see why this trick works. Let V1 up through Vn be the eigenvectors of A with these particular eigenvalues lambda 1 to lambda n respectively. So what that means is that A times V1 is equal to lambda 1 times V1. That's what it means for V1 to be an eigenvector with eigenvalue lambda 1. Similarly, A times V2 is lambda 2 times V2, and so on. Now, suppose it's the case that P inverse times A times P is equal to D. Well, we can just set D equal to P inverse A P, but suppose that D is a diagonal matrix. Now, let's multiply on the left by a P of both sides. So this P times P inverse, it'll cancel, and we're just left with AP on the left, and then P times D on the right. And okay, now let's let P, as before, be the matrix whose columns are the eigenvectors V1, V2, Vn. Now this notation with these tick marks here just means express V1 as a column vector. These are not ones. That's what this comment here is. These dashes, vertical dashes, are not the number 1. Okay. So P is an n by n matrix because we've got n eigenvectors. And then, now let's look at the left-hand side of this equation. A times P. Here's A, and then P is these column vectors that are these eigenvectors. And then, when you think about matrix multiplication, what turns out to be the first column here is A times the column V1. And then, similarly, the last column of this product is going to be, you take your matrix A and multiply by this column vector Vn, and that would be the last column here. And then because the Vi's are eigenvectors, that means A times V1 is lambda times V1, and A times Vn is lambda n times Vn, and so on. And then, if you think about how the matrix multiplication works again, this matrix here turns out to equal this column vector V1 and this column vector Vn formed as a put together as a matrix, and then put a diagonal matrix with lambda 1s along lambda 1, lambda 2 up to lambda n along the diagonal. And then we get, well, this here was our original matrix P, and then if we let D be this diagonal matrix, D, we do get this P times D, where D is the eigenvalues. So we do indeed have AP is equal to PD, with D being a diagonal matrix. So if we use this trick and cook up this matrix P, whose columns are the eigenvectors, now in order for P to have an inverse, those eigenvectors must be linearly independent, and that turns out to be actually a sufficient and necessary condition for A to be diagonalizable, namely that its eigenvectors need to be linearly independent. Let's do an example. So here's this matrix A, and the question is to find a matrix P such that P inverse AP is a diagonal matrix. Now, again, it won't always be possible, but in this case, I know ahead of time that it is possible to find such a matrix because the eigenvectors I've computed beforehand are linearly independent. Anyway, okay. So since A is triangular, finding the eigenvalues is easy. Remember, P is made of eigenvectors. And to find the eigenvectors, first what we have to do is find the eigenvalues. And in the case where the matrix is triangular, the eigenvalues are just the terms on the diagonal. So in this case, there's only 1, and the negative 1 is repeated. So our two eigenvalues are 1 and negative 1. So once we've got the eigenvalues, we next find the eigenvectors. And by definition, the eigenvectors are elements of the null space of A minus lambda I. So let's deal with the case where lambda is equal to 1. We'll deal with the case lambda equals negative 1 shortly. Okay, so lambda is equal to 1. That means we need to compute A minus I. A minus I turns out to be this matrix. And all I did was take the original matrix A, and remember I is just 1s along the diagonals. So I subtracted 1s along the diagonals. Originally there was a 1, 1 minus 1 is 0. Originally there was a negative 1, negative 1 minus 1 is negative 2, and so on. I didn't do anything else to the other entries. Okay, so we've got to find the null space of this matrix. Why? Because here again was the definition of eigenvector. So vector x, so that A times x is equal to lambda x. Move the x over to the other side and factor then an x. And so we have A minus lambda times I times x is equal to 0. And this is what it means for x to be in the null space of this matrix. That means when you multiply the matrix by x, you get 0. Okay, so to find the null space of a matrix, we row reduce. And once doing that, we get, once doing that to this matrix, we get down to here. And so this means that x1, this first line says that x2 is equal to 0. I feel I should have augmented the matrix. I usually work with the augmented matrix. So secretly there should be a column of zeros out over here. But anyway, so x2 is equal to 0 is what the first line says. x3 is equal to 0. And then x1 is a free variable. There's no condition on that. And this is what we have here. x2 is 0, x3 is 0. And so factoring out an x1, we get the null space consists of x1 times this vector 1, 0, 0. So 1, 0, 0 is an eigenvector, and in fact the only eigenvector with eigenvalue 1. Next, let's do the case where our eigenvalue lambda is negative 1. Then lambda is negative 1. A minus lambda I becomes A plus I, and adding 1s to the diagonal entries of A, we get this matrix, and now we need to find the null space of this matrix, and so we row reduce, and when I do that, we get this. This is a pretty simple matrix to row reduce. We just divide the first row by 2, and so then what we get is that, again, this equation here stands for x1 minus x2 plus 4x3 is equal to 0. If I work with the augmented matrix again, there would be a column of zeros here. Okay, and so then this tells us that x1 is equal to x2 minus 4x3. And so x2 and x3 are the free variables. And writing out the solution like so, and factoring out the x2 and x3, I get 2 eigenvectors. These vectors here span the null space of this matrix here. And so finally, collecting our eigenvalues that we found. Previously we had found the eigenvector 1, 0, 0. Now we found these 2 eigenvectors, and So I've added them to this matrix P, and then the diagonal matrix D from the previous slide is going to be the eigenvalues. Just make sure you've lined up them as you've lined up the eigenvectors. So because the eigenvector associated with 1 is, I happen to list first, so that's what I should put first along the diagonal. Then the second and third vectors were the eigenvectors associated to -1, and so that's what I have here. As long as you're consistent, any order is fine. Okay, so yeah, so this is what the matrix P has to be, and then this is what the diagonal matrix D is going to be. And that's our answer for P. Okay, now how is that useful? Well, here's a simple example. Suppose we want to compute a to the 2014. That's a huge number, and it turns out, well, it's much easier to compute exponents of diagonal matrices than non-diagonal matrices. Okay, so we know that P inverse AP is equal to this certain diagonal matrix, and so let's solve this equation for A, because we want to compute A to the 2014. So let's multiply both sides by P, so we get AP is equal to P times D, and then multiply both sides by P inverse to get A is equal to P D P inverse. Alright, and now it turns out that we can easily compute powers of A. So A squared is P D P inverse squared, because A is P D P inverse. And then when I write P D P inverse squared as P D P inverse times another P D P inverse, what happens is that the P inverse here and the P there, they cancel out to the identity, and then the identity disappears, so we get P D squared P inverse. Similarly, A cubed is going to equal P D cubed P inverse. So the same type of cancellation will occur when you write P D P inverse out 3 times instead of just 2 times, and so on. So A to the 2014 is P D to the 2014 times P inverse, and then now D is given by this. Raising this to the raising a diagonal matrix like D to the certain any power like 2014 means just raising each diagonal entry to the 2014. Why? Because you have to think about how matrix multiplication works, and if you stare at how that is, as I kind of indicated here, B squared is, what would the entry here be? It would be, this is in the 1, 1 position, so row 1 times column 1, that's just going to be 1 times 1. The entry here in the row 1, column 2 position is row 1, column 2 dotted, but when you compute that dot product, it will be 1 times 0 plus 0 times 1, negative 1, and that's going to be 0. So you'll get a 0 here, similarly you'll get zeros elsewhere. Let's see what happens in this position, row 2, column 2. So we take row 2, column 2, dot them. That's taking this entry and squaring it, and likewise for here. So that's the general pattern, that when you multiply two diagonal matrices, their respective entries or corresponding entries just multiply. So taking this diagonal matrix to the 2014 power is just raising each of these diagonal entries to the 2014 power, and it happens, you get the identity matrix, because -1 to an even power is 1, and so then you get P times P inverse, which is the identity matrix. So A to the 2014 happens to be an identity matrix.